Hi, and welcome to our presentation. I'm Henning Jolivet, and my partner is Aaron O'Brien. We're both players on the SU men's soccer team, and we wanted to pursue a project that was in line with our passion for soccer. On top of that, we wanted to look at statistics and results of our favorite soccer league, the English Premier League, to see if there were any trends to uncover. So we chose the pretty cut and dry problem of predicting the odds of a home team winning or not losing based on game stats. Our data was comprised of the stats of every game in the English Premier League from the 2006-07 to the 2018-19 season. The original dataset was comprised of 31 columns and 4,938 rows, but we modified it so that it was in the end comprised of 29 columns and 4,938 rows. I'll get into this change in columns next. On the left, we have the original features, and on the right, we have the features after our modification. The ones in red were either deleted or used for a different purpose, and the ones in the green were added. Goals was taken out because if it were included, the machine learning algorithms would be 100% accurate, since it would know that if one team scored 3 goals and the other just 1, the first team would win. We wanted to just purely predict the results on stats other than the goals scored. The match week was taken out because it was not relevant and the season became the index. Win and non-loss became binary values to indicate either a win or non-loss of the home team. The rest of the data was left untouched. In terms of descriptive statistics, we decided to find the averages of the columns and came up with these results. We can see that some features are higher for the home teams for wins and non-losses when compared to the average, such as home touch, home possession, home shots, and lower values for away pass and away touch. Might suggest a good strategy might be to purely break up the opponent's play. Next, we wanted to see how these features were correlated. We can see that some features are strongly correlated, such as home goals, home shots on target, home passes, home possession, home passes, home touches, and so on. And we can see that others are weakly correlated, such as home shots on target, home possession, and home shots. We also uncovered some interesting observations, like the more shots a home team takes, the more shots the away team takes. This would lead to people thinking that a home team would rather take fewer shots with higher quality, since the more shots they take, the more shots the away team gets. And along with that are other interesting facts, such as more passes lead to more touches on the ball, which is ball hogging, which is counterintuitive. More passes lead to a higher level of possession. The more possession you have, the more corners you will be granted. More possession doesn't necessarily mean more goal scoring opportunities, and the number of completed passes isn't correlated with the number of total shots taken. Next, we decided to use a heat map to visualize the correlation matrix. Here we can see certain distinct areas that are more important when predicting a result. This heat map further validates our belief that certain features should be weighed more heavily. In terms of selecting our model, we chose to put every model to the test. There are 4 versions of the table below, as we created 4 different datasets that included different features for the X and Y values. We then trained the data in the 4 datasets with every model and found their metrics. We had best results with the SVC model, so we chose to move forward with that one. As you can see, the models on top don't do very well. However, the lower models do. In this case, SVM predicted the result of a home non-loss with 79% accuracy. In terms of justification, again, as you can see, the SVC/SVM model outperformed the others in this run, as well as on all the other model comparison tests as well.
For feature scaling and engineering, we used feature scaling for our ridge and lasso regression using min-max scalars and also poly features for ridge. We used a standard scalar for our KNN tests and a min-max scalar for our ANN tests. For using feature scaling in ridge and poly features for ridge, the difference is minimal, but there was a smaller difference overall in the 4 data sets. The same is not true for lasso, as in fact, using feature scaling would not be recommended if the model selected had been lasso. KNN having standard scalar helped with normalizing the data, as did using min-max for the ANN. We tested the parameter tuning for a couple of our different models, but the focus of this presentation is on the model we selected, which was the SVC model. We wanted to see which C parameter would be the most accurate. We tested using C as 0.1, 0.5, 1, and 5 to see if one of these had a smaller difference between the training and test data sets, while keeping a high level of accuracy. We realized that the different C values can either increase or decrease the accuracy on the test data by plus or minus 4%. Our tuning results show that the C value of 0.1, 1, and 5 had the best trade-off of prediction accuracy and error, depending on the input variables. For our evaluation metrics, we used two different factors to decide. The first one was, did they have a high or low level of accuracy? We used a dummy predictive model to decide this, which you will see in a bit. So overall, the best ones with the highest level of accuracies were KNN decision tree, SVC, GMB, random forest, or GB decision tree, as they both had above accuracy compared to the dummy predictive model. After that, the evaluation metrics were which had the closest in terms of the training and test data sets, or the smallest error. That's how we ended up selecting the SVC model. As mentioned, we used a dummy predictive model to make sure the accuracy for the model we selected was higher. Based on our dummy accuracy score, anything above about 56% was available for selection, including the SVC model we selected. Our predictive errors depended on which specific models we were doing. The ones with lower training and test data sets tended to focus more on the test data sets and as such had a higher chance of underfitting the model. These were the simpler models for the most part and experienced higher bias versus variance. Our more complex models had a higher chance of overfitting and as such experienced higher variance than bias versus the case of the underfitting models. Overall, most of our models had some form of bias or variance showed predictive errors, but there were a few that showed much less bias or variance than the majority of the models, such as the SVC model we selected. Our coding issues came with model selection and selecting the correct features in the model, and with parameter tuning in terms of deciding how to use it. We ended up deciding that using only binary at first for SVC, and then after getting results, seeing if parameter tuning would change what model we would decide on was the best way to go about it. Finally, due to the size of the file and due to the difficulty with at-home Wi-Fi, sharing the file and any updates to it became increasingly difficult as the project continued into its later stages. One way we solved this was by sharing snippets of the code, meaning that we would share the SVC part or the KNN part or a parameter tuning aspect of it so that we could edit that, finalize that, make sure it looked good, and then add it to the master file later so we didn't have to deal with the increasingly large file at a home Wi-Fi where it's not as strong as where we're at school. We found we had three interesting findings. The first was the more shots a home team takes, the more shots the away team takes. What this means is teams tend to be more open if they're trying to take more shots, and thus they are conceding more shots, which means a higher chance they actually concede. What they want to do is take fewer shots with higher quality, since that way they'll have a higher chance of scoring because more of their shots will end up on target, but also it means the less shots the away team will get, which means the less chance they have of conceding. The other thing which we will see in our results was knowing which team are playing yields a slightly better result in predicting the results of the match. This shows that sometimes the teams that are playing are sometimes more important than just pure game statistics in predicting the results. And the last thing was home teams are more focused on build-up play while away teams are more focused on counterattacks. We learned this by looking at the correlation between possession and shots. Home team had a higher correlation between possession and shots than away teams, which means away teams don't need as much possession to get their shots off, which means they're more focused on the counterattacking aspect of their game. As you can see from our results, our second interesting finding is proven here is knowing a home win with known home and away team or a home non-loss, which just means a tie or a win, with known home and away team are both higher than the exact same data frames but with anonymous team names. It also shows that having a non-loss will have a higher accuracy score because we can predict both a tie and a win, as both of those are around 81%, one just below, one just over, while the home win with anonymous team names and the home win with known home and away team names are over 75% but below 80%. Our experience with this project was interesting. We had a ton of success in our opinion with the final results once we tuned parameters for the SVC models and even had a few others still had minimal errors, but there were some models that definitely had issues at the same time. As kind of mentioned with our project issues, the toughest part of this experience was definitely trying to work outside of a school environment, as we don't have strong Wi-Fi and we've never worked with this large a data file. So sharing the updates we made to the program was difficult at times because downloading the new file could take excessively long. We, as mentioned, found a way around this eventually to continue with the success we found in the original code of our project.